I have never used this thing.
Really? Perfect.
I am a natural. What
When
do
it's green, it's transmitting, so everyone can hear you on Zoom right now. Let's try.
Can you check that we are live, Eda? Let's check. We are live. Okay. Can you guys hear me well? Let's get it started. Okay, perfect. Hello, everyone. Welcome to this problem-solving session of digital design computer architecture. Sorry for the delay. We had some infrastructure issue, but everything is sorted out now. So the schedule for today is that first we will solve some example sample questions. And during that, we will also answer to some questions that you may have regarding that topic and that question. Around 3 p.m. or 3:30, Frank will also join us. And good. Yeah, good that you like your instructor. And then basically you can ask almost, I guess, any questions you have from Frank, and he will be here to help you. I will be also staying until 3:45. Then I need to leave because of a meeting. So the first question, I think Konstantina will start solving. Thank you.
Hello, everyone. My name is Konstantina, and I'm going to go through the first problem that has to do with arithmetic representation. So we have prepared some questions. The first one, we're going to give you 4 numbers, either in a decimal or hexadecimal notation, and you will be asked to write the corresponding binary number using the indicated format. So the first one would be to transform this number. Okay. Yeah, right. Thank you. So this one, it's a -6 in the decimal, and we need to transform it in 6-bit signed magnitude. So what we're going to do about this case, we have available 6 bits. The signed magnitude means that we're going to utilize the most significant bit to actually show what is the sign. In this case, we have a negative number. Therefore, the most significant bits would be 1. The rest of the bits are going to be utilized for the absolute value of 6. So this would be the solution of this question. Any questions? Okay. So we move on to the next number. So we have 37, again, decimal, and we want to represent it using 6 bits and unsigned. So again, we have 6 bits available. What we're going to do is to write 37 as a sum of powers of 2. So 37 is 32 plus 4 plus 1. This indicates us the position in which the AC should go. So since we have an ace, we're going to have 1 here, 0, 4, and then we're going to have an ace on the most significant for the 32. Okay. Is this clear? Okay. Now we move on to the next number. minus 28 in the decimal, and we want to represent it again using 6 bits. But this time we're going to use 2's complement. So since we're using 2's complement, first we're going to utilize the absolute value of this number. We have 28. Again, we're going to write it as a sum of powers of 2. This would be 16 plus 8 plus 4. And utilize 6 bits for that purpose. So we have 4, 8, and 16. So this is 28. Now, according to 2's complement, first, the algorithm that we know to transform it, first we're going to complement this binary number. And now we're going to add 1. So 1 plus 1, it's 0, propagates, 0, 1. So this is the solution. There is also an alternative, quicker option that you can use. Basically, you're going to find the first case in the absolute value in binary format and start to complement the number from that bit and onwards. You can also, once you've solved such a question, you can validate your result by making sure that this number is actually minus 28. So we're going to have to translate all of these bits as usually, but the most significant one would be minus 32 in this one. So minus 32 plus 4, you get minus 28. Okay, now we go to the next one. We have 2b in hexadecimal format, and we want again to illustrate this, represent it as a 6-bit unsigned. First, we're going to write it in a binary format. So we have 2. We're going to use 4 bits for 2. And b, which is 11. Now we only want to use 6 bits. In this case, of course, it fits. So the answer would be this one. Okay. So I'm showing a little bit all the examples that we just did. Do you have any questions on those? No? Good. Then we move on to the next part of this question that actually is still on arithmetic representation. But we're going to ask you to decide if the following statements are true or false. So I'm going to write here the first one. Yes.
Let me read it.
About the previous one?
So what would have happened if the bits were more than 6? Not sure if.
I think that the question would be wrong. We will have an overflow. And for example, if you had right here an ace, 6 bits are not enough to represent it. So you would have an issue, like an error in your computations, basically. Mm-hmm. Yeah. They wouldn't ask you to do that in the terms of an exam, of course. And when you're writing code, you should be able to not do this mistake.
And folks over Zoom, you can just actually speak up and ask your questions. Okay. So, thank you.
Actually, can I use maybe the, I have here the, maybe people can make it out, but these are the questions. So the first one is right here. So both 2's complement and sign magnitude representation can be used to represent negative numbers in binary. The question if this is true or false. Of course, it is true. We can represent negative numbers with both these representations. Of course, in each case, we can represent a different range of numbers. And usually, we utilize in like the computer systems 2's complement. The next one, using n bits, it is possible to represent 2 in the power of n different numbers when an unsigned number system is used. So this is also true. What we can do with n bits is essentially represent all numbers starting from 0 in an unsigned, of course, representation, up until 2 raised to the n minus 1, which is actually exactly 2 powered at n. And last one, while there are methods to represent both positive and negative integers, it is not possible to represent fractions or real numbers using binary numbers. Is this true or false? So this one is actually false. You can represent both fixed point as well as floating point numbers by using a specified number of bits for each part of the number, essentially. So that would be the end of the exercise regarding arithmetic representation. So now we can move on to the next one. Oh, yeah, sorry.
So roughly how many points would these exercises give you in the exam?
Yeah, maybe you're...
I think you better to ask this question from fact. Yeah, you will be here.
Okay.
We actually did some. So I think based on, so our plan is to, for every 2 minutes, you will get around 1 point. So that's our criteria to design the points and questions. Because the exam is designed to have like around 2 hours time, 140. I mean, you have some extra time for sure, like 3 hours. And so the exam also is 70 points. So you can make some maths. Yeah, yeah.
It's not on.
Is it now on? Yeah. Yeah. Okay. So the next question is about MIPS assembly language. It's actually quite simple. And for the exam, we will also give you, the list of instructions. So you will have also that information during the exam. So the first part is that you're given a code of MIPS. And the first part is asking that briefly explain what the above MIPS assembly code does. So if you check this code, we need to go like instruction by instruction. So you know that here, so this register T0 will be initialized to 8 because the $0 plus 8 is going to be 8. And then we have XOR of basically register S0. So since we are XORing S0 with itself, then the result would be 0. So essentially this XOR means that we are initializing register S0 to 0. And then we have this branch equal instruction that is gonna control the loop, the number of iterations that we are in that loop. So the condition is based on register T0 and the register 0, which is 0 constantly. So meaning that when T0 is 0, we are done. But in the beginning, we are not done because T0 is 8, actually. So then we have two load words. The first one loads from this address, which is addition. So the effective address is going to be the addition of 0 and value 4. So you load from this address 00004, the value from that memory to T1. And then the next instruction, you will again, load from this address 024 to T2. And then basically, essentially, we are adding T1 and T2. So the first addition is T1 and S0, which since S0 is actually 0, so it's going to be T1 to T3. And then we add T2 and T3 to S0. So essentially, after the first iteration, S0 is going to have T1 plus T2. And then we minus T0, and then we jump. So what you need to explain for the first step is actually the number of iterations of this loop, which is going to be 8, because we initialize T0 to 8, and every iteration we decrement T0. So it's going to be 8 iterations. And then you also need to say what's happening per iteration that I already mentioned. So that would be the answer to the first part. Any question? Yes.
The loop turns out to, for example, generate the Gaussian formula. Do we need to also realize that it is the Gaussian formula that is created by it, or is it enough to say just adding those registers and those registers?
So we are not testing your background in mathematics or something like that. So I don't think you really need to say that. If the code is simple, like doing a sorting algorithm or adding a different entry of an array, for example, then yes, better to say that, yeah, this code actually make an average, calculates the average of this array elements, or does sorting of this array, for example, a vector. But if it needs some more mathematics or something, some fancy things, no, you don't really need to say it. Yeah. So I would say normally, no, you don't need to say anything. Any other questions? Okay, great. So, so once you've done part A, actually part B is also quite easy. Assuming the data at memory location, basically 04 is decimal 16, and at memory location 024 is decimal 32. Actually, part B is giving you some hint to answer part 0 as well, but anyway. So what will be the content of the register S0 in hexadecimal when the program execution jumps to dawn? So what you need to do, what you need to know is that the code does these iterations 8 times. So it's just 8 times these values, basically, 16 plus 32. So you calculate this, and then you make it to hexadecimal. Easy, right? Okay. Question? No. And part C. Briefly explain the 3 different MIPS instruction types, R, I, J, and show one instruction of each type from example code above. So yeah, so you know that R type instructions, they usually, they have operands from registers. So they usually have 3 register operands. So that's one key thing about R format that you need to mention. If you want to go deeper, you can say that, I don't know, the opcode for R type is 0, and then we need to differentiate between different R type from function code. And mostly R type is using for arithmetic operations, this stuff. So, but based on the solution, I think only saying that operands from 3 registers would be enough. 2 are source operands and 1 is destination operand. So an example from the code. So we had this XOR R type, right? So this one is an R type instruction. So for I type, so it's immediate format. So it's used for instructions that we need some immediate value. So you need to mention that the immediate part of this I type is actually 16 bits. Whether you want to do that immediate value for an arithmetic operation, like add I X or I and I, or you want to use that immediate for your some branch instruction, like conditional branches, like branch equal, branch not equal, or so on and so forth. So that would be the answer to this, what is I type. And from this code, we have this add I, BEQ, even load word. I mean, there are many examples of I type, right? And J type is actually mostly using for unconditional jumps. And we have 26 bits to specify the address, the destination address of the jump. So still with J type, the address for the destination address of the jump is still a bit PC relative, because you're going to use the 4 most significant bits of the current PC as is, and then add this 26 bits plus 2 0, because everything is divided by 4. So in the end, it's still a bit PC relative, but is much you have much more freedom compared to immediate address in I type, because in I type you need to basically just you need to calculate the offset between the destination and the current PC. So that would be pretty much it. Like the jump J is for unconditional jumps, and we have 26 bits to define the destination address. And in our example code, we have this jump loop, which is a J-type instruction. With that, I think that's pretty much it. Any question? Okay, cool. Good luck.
For me? No.
No. I mean.
Okay. We're going to solve an extremely simple Verilog question. So this question is asking you to write the Verilog code for the module that you see here. You have this block diagram. It says this block is called controller and has 6 1-bit inputs that you can see here on this side, and one 1-bit output. That's the result. It contains 2 modules, 2 instantiations of the comb module, combinatorial, I guess. And the following, it says, is the declaration of the comb module. It's on the next page. We're going to go here. I cannot display both of them at the same time, so unfortunate. And this is what the comb module looks like. It has 3 inputs and 1 output. You need to know this because you're going to instantiate it in your code, but you don't need to know what's inside of it. So I'll just start writing this. There are some notes here, such as the flip-flop and the multiplexer will not be instantiated. You will have to write the corresponding Verilog code. The flip-flop uses an asynchronous reset, so this is important. And yeah, well, a note that Verilog is case sensitive. That means, I think, for example, here, we say that the module, the block is called controller with a capitalized C, so you need to take that into consideration. Okay, so let's start. So this is obviously going to start with a module definition of controller. Now this is going to take some time. You're going to have 6. Let's start with inputs and outputs. Obviously, right? You can see from here. Okay, we have a reset, 3 input bits. They're named N1, N2, and N3. 1 select signal and a clock signal. So we'll write them, starting with reset. Then more inputs are 1-bit inputs. They're N1 with a capital I. More inputs. You can write them next to each other. Oh, See, I made a mistake. That's deducting already 10 points or something. No. Select signal. I don't think I'll be able to fit this whole module definition here, but we'll see. Can you still see this? Yes. And an output. Well, I guess we will define it as a register. You don't have to do this. There are multiple solutions. What's that? Yes. I forgot the clock signal. So we'll add it somewhere here. You're allowed to do this in the exam. Yeah, what else? Let me see. So we have the inputs and the outputs. We can instantiate the combinational logic blocks here, because it's going to be relatively easy. So this will be, you can see their names here as well, right? Instantiation left, inst left, and inst right. Those will be their names. So how do we instantiate modules? We write the module name, that's com. And then we have, well, I'll need to fit some intermediate signals there, so I don't have space anymore. Interesting, how do I solve this? Well, let's just do this. You assume whatever I write here is actually in between module input output definitions and the combinational block, right? So let's continue with combinational. Inst left, that's the module name, that's the name of the instantiation, not the, sorry, that's not the module name, that's the instance name, yes.
Are we allowed to input parameters, in other words, just one input keyword and three parameters?
Like this one? Yeah, this works. If they're defined the same way, they're single bit inputs. You can try this, but I don't think it will. What won't work is something like this. Right? So you have in the same line different signals with different bus widths. So let's just get rid of this. Yeah, so we'll connect our signals to this. If you remember from this picture, it has three inputs. Well, the module definition is up here. Yeah. So input A, B, C. We need to connect in 1 to A, something I can see from here. In 1 goes to A, in 2 goes to B, in 3 goes to C. And the reverse, it's in input 1 goes to C in the other combinational block. Input B goes, input 2 goes to B, and input 3 goes to A. So their order is reversed. So for this one, we will connect in 1 here, connect in 2 to B, and then C. These are dots here. You can see them. And then C will receive in 3. And there will be an output also from this module. It's output Z. That's not a 2, that's a Z. There's like a syntax error here of a parenthesis that I accidentally put, which I just removed. All right. Yes, there's a question over there. Yes. Probably yes. Ask Frank, right, to make sure. Well, so simple errors like this one, you would notice this and remove it, right? But yeah, I guess if it was me, You will be fine. I can say that. Okay, there are too many questions now. You have something over there.
Will you get points deducted for using positional arguments instead of keyword arguments in the instantiation?
No, no, I think it will be fine. Some more questions here. Yeah. I wouldn't do that. I mean, here it's quite explicit that these are separate signals, right? Just follow, I would follow this. Okay. So this output of this module will have to go to an intermediate signal that we will call left. That is here, wire left. Right, it goes here. I made a mistake. Wait, yes. I fixed the mistake, by the way. That was this semicolon. Yeah, don't make these mistakes. Okay, we're done with the first module. Yeah, so we'll go with the second one. In stride, I'll go very quickly here. As I said again, the inputs order, the order of the inputs are reversed. So C gets in one, and then you connect right to this C. I define it here. Now what happens? So now we're done with this part of our module. I'm just gonna do this. And then we now have a mux to deal with. So this mux will select either the wire called left or right. And you can do this in many ways, but one way you can do this is just using this. If you remember, what's going on? Wait. Already started with assign, so that means I have to define another wire here. That's going to be mux output. Again, based on this signal name here, right? So we'll assign to mux out. We're instantiating a mux here using this ternary, I think the ternary operator, right? You can correct me if I'm wrong, but I believe this is what it's called. What this is going to do is, if the select signal is set, it will select right. If the select signal is not set, it will select left. Yes.
So do we need to give everything names? Because in the other code, this is required.
Like what?
Yeah, like the wires and the instances of the combination logic of the mass.
So this one you don't want to name, for example. I would just name it because, I mean, you have the name in the module definition. Just try to stick to it. Yeah.
If I drop the names, I would definitely save 1/3 of the time.
You can do it much faster than I'm doing it here, by the way, probably. So don't worry about time so much, I think. But stick to what the question gives you as a module definition as much as possible. Just to not get surprised in the end. We're done with the mux. So now we only have the flip-flop to deal with. That is this block here. Again, multiple ways you can do this, but we will use an always block, one single block. Yes, is there a question? No. Okay. This has to be triggered in a triggered with the passage of the clock, right? The clock signal. Now, because the question asks us to do an asynchronous reset, what I'm going to do here is I'm going to trigger this block with the passage of the reset signal as well. And inside, I'll have an if. Okay, now there's a problem here. I'm hearing myself back. No, okay. No longer hearing myself back. So if the reset signal is set, then the output has to be 0. You can do it like this. You can set, so we had already defined the output result as a register, so we can make assignments to it inside this always block. What we're gonna do is just that. Result will be a non-blocking assignment with a single bit 0. And otherwise, you will basically assign whatever the max output signal is to the value of result. Well, I mean, this is just some simple, I guess, detail. No, well, it's not simple. It's just the detail. You don't have to write AND here, but you could write it if you want, because this is one-liner inside an always block. And then obviously you need to end the module definition. That should be enough for this module. Do you have any questions now? Yes. That's true. See, you caught another mistake of mine. If you want end, you need begin, yes. Cool. Any other questions? Should be able to do this in 2 minutes in the exam. No. Probably you can. I mean, you're gonna do it much faster than me anyways. I think I'm done, so who's next? There's a question, yes.
Okay, so he doesn't have a mic. This is the question.
Yes. Can you?
From the output. So it's a direct message to me.
Okay.
Can the output result be declared as reg as long as it is used in an always block? If it is not in the always block, it could be right?
You can still define it, but you cannot make like an assignment like this to result right now, because it's not a wire. So this statement would be incorrect outside of a, this is just an example, outside of an always block. Right now you cannot do this, but you could have result and not have this, and not have anything assigned to it as well. I think Vivad or your compilation tool would eventually warn you or lead to some sort of error, but you can have it. Yes. So you can write 0. Yeah. That's a good one. Well, I actually don't know according to Verilog standard what the standard format is, but I remember in Vivada at least having those sort of number formats without the when I don't explicitly state it, I remember them being interpreted as decimal values. But you can check at home. Yeah. Yes. The question that I answered just before this, can you, what was it this?
Can the output result? Can the output result be declared as reg as long as it is used in an always block?
Can the output result?
Not in the always block, it could be right?
So if it's not in the always, yes. So can you? This is I cannot repeat this question. I cannot understand it. Yeah. So if you define the result like this, like a register, like as a register, are you allowed to not have any assignment to it in an always block? Which should be yes, but you cannot do this also if you have defined result as a wire. Sorry, as a register.
There's also one more.
Yeah. Yeah, we answered that. So the question is, can you use AND here without begin? No. Yeah. Yes.
Can I already assign the value directly to result instead of putting in max
So you want to do like the if condition checking here. So the question is, can I just sort of move this logic inside the always block by not having this mux instantiated here explicitly? Again, I wouldn't do it, but you can do it. And if you're sure that it's going to be synthesized as a mux, it's fine. Yeah. The safest method declare muxes are like this. Okay, cool, I'm done. You already?
Okay, this works, great. So I'm gonna be showing two of the, oh, can I hear myself double? No? I'm going to be doing two of the exercise. So first the FSM. Yeah, I'm not sure. Maybe I'm just not used to it anymore. Yeah, so I'm going to be doing the FSM one first and then a Boolean logic question. Let's start with the FSM. So here you're given a FSM of either milli or more type. You're supposed to decide what it is, and then you're supposed to change it somehow later. Well, I guess I don't need to introduce FSMs to you anymore. Clearly, this is a mealy type FSM. Yes. There we go. Thanks. Yeah, so this is clearly a mealy type FSM. Reason being, the output depends also on the current input. A more type FSM, the output would be only depend on the input, something like this here, out 0, 1. But that's not the case here, right? You have an output per edge. Okay. I assume there's no question here. Next, you're given a state encoding table, and then you're supposed to kind of write down all these transitions into this table. So I'm thinking maybe I'll start with the first few lines and then skip to the solution because it's not really that interesting once you start. So basically, you take one of the, you can see this, yes, okay. So you're thinking perhaps of the init state over here, right? You take the present state is 1, 1, 1, 1 for init. Then for the input 0, we would go to the state 0, which has encoding 0, 0, 0, with the output on this edge 0, 0. If you had gotten the input 1 instead, so same starting state, input 1, your next state would be mid. Mid has the encoding 1, 1, 0. Sorry, 1, 0, 0. And the output of that edge is 0, 1. Okay. Is that good? Should I do the entire table? Yeah, no, okay. Thank you. Okay, I think this one's a bit more interesting. If you've not seen it before, if you've seen it before, it's not that interesting. You're supposed to here convert to a different type of FSM. Oh, that's where I can hear myself. Can I mute this? There we go. Much better. So clearly we identified earlier this was a mealy type FSM. So now we're supposed to make it into a more type FSM. So as you recall, and as I mentioned, the more type FSM means the outputs would be per state, not per edge. So the key difficulty here is some of these edges, if we were to take this exact FSM, just write the outputs into the states, we might have some states, for example, like this one, that has 2 ingoing edges that are supposed to result in different outputs. But in a more type FSM, the same state can only produce 1 output. So we need to come up with a solution there. Solution is quite simple. You introduce multiple states if you have multiple ingoing edges with different outputs. Let me show what I mean here. So we take the same state and we just add to the name of the state its output on its edges. So sorry, it's in the output on its ingoing edges. So the init state has only 1 ingoing edge with the output 0, 0. So we call this state init 0, 0. Never forget the reset signal that always costs points, and it's so disappointing in the end. Also when correcting these exercises. Okay, and from here we can go to the 0 state with the output 0, 0. So just to highlight this again, because the output here is 0, 0, we call the state 0, 0, 0. Right? I'm just implying here that this is also the output of the state. Probably in your solution, to be clear, you should write a sentence like, oh, the output in these states is always the second line, something like that. Clearly identify your outputs, basically. Okay, so this edge is on the input 0. The output is 0, 0 on that state. That's all good. Now, from here, if you get another 0 as input, we would go back to the same state and give the output 0, 0. So this works with the same state, no problem. Then if we get a 1, we go to the 1 state, and we have the output 1, 0 on that edge. Okay. And then if we get a 0 in that state, we go back up here. Okay, so far so good. I kind of just literally copied the diagram from over here so far. And now when we introduce this path here, you'll see what we kind of need to change. So from init, we go to mid with output 0, 1. So we call the state mid 0, 1. Okay, it's only 1 bit. And if from here we get another 0, now we have the output 0, 1 in the 1 state, right? Which is incompatible what we have over here. Can you see this? Here we're supposed to be producing the output 0, 1 in the state 1, but over here our state 1 has the output 1, 0 from what we did here earlier. So the quite simple solution is to just introduce an additional 1 state. This additional 1 state has the output 0, 1. Okay, so we had to duplicate one of our states. Frank is here. Hello, Frank. Okay, we have these 2 1 states now. Don't forget to add the backwards edge up here. If we get another 0, yeah, this is this edge. Then we get another 1. We go to the 2 state with output 1, 1. And on a 0, we go up here. On a 1, we remain. And I think that's about it. Yeah. So the only trick or challenge here is, of course, you need to realize that you're supposed to do a Moore type FSM, and then you hear how to duplicate these states to be able to give different outputs for these different ingoing edges. That makes sense? There's a question. Yes. You should. Okay, let me repeat the question. Thank you. Are you supposed to name the states differently? So these two one states. Yes, they should be named separately. You shouldn't have two states with the same name. What I did here essentially is interpret these as strings, yes? And then additionally to that, what you should be writing here is that this also has the output 0, 1, the output 1, 0 for each state, of course. Yeah? Oh no. Here? Thank you. More questions? From mid to 2, yes. See, more questions. I did a terrible job here. Over 1, yes. Hopefully that didn't hinder your understanding of the concept.
Do we have to name the states, or could we just write the outputs as the name?
Well, I guess worst case you could number your states or something like that, but yeah, Frank says no. So
No, let me be clear. There are some state machines that are special, where the state is directly the output. We didn't talk about that. We call them Memory-Centric. It's a special thing where, you know, the states are uniquely coded that they become outputs. If that's the case, that would be okay, because every state is unique. But you are naming the states not because you have to, because it makes your life easier, because you will end up writing code. And, you know, you will write a case statement, and you don't want to say case 0010 or something like that. It might be easy for you because you're a super geek, but you will have friends that will have to work with your code, interact with the code, and do things. And it's not good at all. I mean, it doesn't have benefits. Right? No? Who asked the question? Are you coming? Is it okay? Give names, give good names so that, you know, your code is easily readable. That's the main message. Regardless of how many points you might lose or, you know.
thanks. Yeah, makes sense if you're programming, I guess. Another question, yes.
So this is when we are going from needed to 4, right? And what happens if we go from more to these? Like here, you're allowed to basically duplicate the states that had 2 different outputs in terms of there are like 2 different inputs. Like if you're going the back way, so we have like, are we also allowed to merge the 2 states into one, because we can do it much more efficiently if you're switching from more to nearly?
Okay, let me be clear. This is not some secret thing you're allowed to do when I just duplicated states here. Yeah, you're just picking one of a million ways of just creating an equivalent FSM. There's no, or you're allowed to use rule X. The master solution actually has a slightly different FSM that doesn't exactly use the strategy that I showed you. So in the end, you need to have an equivalent FSM, and it should be clear that it's the same FSM still. Going back is typically easier because you could always have the same literal FSM actually. And then yes, maybe you could actually simplify it. But I guess this is not something we do here in our exercises. In theoretical computer science, you for sure have such exercises. Yeah.
Do we have to name the states exactly the
I mean, if Frank decides you have to, you have to. For the same argument, I'd say no. I guess the important bit in the end is that you need to have an equivalent FSM, right? For the same inputs, it should produce the same outputs. Apart from that, everything else is convention, helping yourself program, or helping whoever is correcting your solution to give you good points.
I mean, that's a good point, right? I mean, somebody is correcting your exam, you write something very fancy, and the assistant is not able to decipher it. And now you get up, and you know, at some point might be that they have a template, they cannot recognize match them, and they don't, I mean, it's not as important for the people correcting the exam as it is for you, right? And then it's not maybe a huge problem. You get a slightly lower grade, and then there is a correction session. You go there, there's a longer argument, and you make your point. You say, I'm so much cleverer than you. I did this, but you didn't understand it. And then you have to write letters to the study secretary to correct your grade. Is that really necessary is the question. Okay? I mean, make life easier for yourself or the others. It's generally helpful when you're writing code to, you know, if you're modifying something from one to the other one, trying to keep some correspondence points helps other people also to replicate.
Another question. You're asking if every Moore machine can be converted into a mealy machine. And yes, they have the same. Yes, in theoretical computer science, you'll be proving all of these things, and what cannot be turned into each other. But yes.
So basically, Moore and mealy are just questions.
They're different representations for the same functionality. You could write a Verilog module that does the same stuff, right? That's you could call this an encoding of the same logic in the end.
Very practical question on the exam. When we get the exam papers, they will probably be stitched together. And when we replicate the image from one page to another page, can we just pull it out, this page, so we can have it side by side? Or is that not allowed?
So that one I can take it.
You need a microphone.
You can shout into Frank's microphone.
You can shout into my microphone.
So, I mean, try to not do that as much as possible, but we will also bring some staple that we will staple your exam. But it's important that you tell us when we are collecting the exam such that we staple your exam. Otherwise, we may lose your papers.
Not on purpose, not on purpose, okay? Don't be too violent, you know, don't tear things.
Another question.
For the mealy machine, you have to define what happens with the output on reset, because in the left diagram, it is not specified what the output is after reset, before any other position.
That's true, but by definition, a Moore type FSM has an output in the reset state, in the init state or whatever, right? It has an output in every state. They're, in that sense, I guess they're not 100% equivalent. The way to interpret these states essentially is to think of the output on the edge of a mealy machine as equivalent to the output on the state of the Moore machine. So really the output you're getting here is the output that's over here, right? Yeah, it's essentially the first cycle of your execution that's undefined, essentially. But, well, in practice, it's not an issue, I guess. Happy? Cool. Then let's go to this beautiful table. So it starts easy. You're giving this logic function. And okay, it has some x's in here. Yeah, just 2 of them. So this is third. Yeah, there. So the first question is, what does an x mean in a logic function? An x in a logic function means it can be anything. Okay, it's not required to be either 1 or 0 for your circuitry. So to optimize your logic functions, you can choose. So can be either 0 or 1. That's the meaning of x. Yes. Okay. And now a friend of yours has determined the following Boolean equation. But he's not sure if it is correct. I guess you can guess if the question is like that, it is not correct. So you're supposed to verify if this is correct, and if it's not correct, why? So the way you can essentially compare such a equation to a logic table that you're getting is you just go through the terms and you cross out if it covers the case that you needed to cover. So when it's in this representation, so was it the minimum of maximums, you go through each term. So you have, the first term is B or D. So you go through all these entries here. And if any of them, well, you go through all cases where this term is not fulfilled, right? Which if this ends up being logic 0, then that forces the entire equation to be logic 0. So you can just go through here and make sure that every time, so for example, we have B0, D0, that ensures this must be 0 by itself already. Does that make sense? Okay, so that means I'll just cross out the 0, right? This is kind of covered by this equation. Let's find the next one. B0, D0 is here, okay. This is also covered. B0, D0 here, this is covered. B0, D0, this is covered. Okay. Next one, not B, not C, or not C. So this means over here, we're looking for cases where they're both 1. So we're looking for 1, 1. Okay, this 0 is covered. 1, 1, this 0 is covered. 1, 1, this 0 is covered. 1, 1, this 0 is covered. Is the strategy clear that I'm applying? Good. Then we have A, not C. So we're looking for 0 in the A and a 1 in the C. So we have that over here. Oh, this is already covered, okay. What else? Okay, this is also already covered. This is also already covered. Let's see. Do we have all of them? Oh, it covers this one additionally. Brings up the question, do we need this one? So this might be an unnecessary one. Let me check the equation. Did I make a mistake already? Did you spot a mistake? Hopefully not. Well, I lost my solution paper. That makes it more difficult. But yeah, I'm suspecting this one might be unnecessary here because the only reason you have it is that it covers one of your axes. That's kind of not needed. Okay, then we have not A, B, or D. So you go through here and you look for cases where you have A, B, 1, B and D be 0. So let's see down here. So this case is already covered, and this case is also already covered. So this one's definitely unnecessary, which makes sense because the first equation covers this one. So this is just redundant. Okay, then we have A, B, or C, not C. So we look for cases where this is 0, this is 0, this is 1. Thank you. Oh, indeed. It was not a mistake. We were entirely right. This is redundant. Great. Okay, so we're looking for these cases here. 0, 0, 1. This is already covered. 0, 0, 1. This is, well, irrelevant for the x. And then there's no more 0, 0, 1. So this 2 is redundant. Okay, finally, A, C, or not D. So we're looking for a case where this is 0, 0, 1. This seems to be wrong, right? This equation over here would for this input 0, 0, 1 would force the entire equation to be 0, but the output is supposed to be 1. So this one is just plain wrong. The second case would hit the x, but we don't care about the x anyway. Okay, so now we've figured out that some of these are redundant, and we've also figured out which zeros are covered. Let's see, did the equations that we have cover all the zeros? No, right? The 0 here is missing. So we're missing one more equation over here that gives us something like let's see, what's it supposed to be? Is it not A? Yes, thank you. Not B, C, and D. And with that equation, it will cover that 0, and then we will be good. Okay, so we found 3 redundant ones, one that's just wrong, and one that's missing. Hopefully there's many points for this exercise. It takes a long time. Okay, so far so good. Questions, aside from possible mistakes I made? No? Yes? Are we in a hurry?
No.
Good.
How many points?
I'm not sure. This. Yeah. So now we're supposed to derive optimized Boolean equations in the sum of products form. So get a nice. There's a question.
For the lost, don't you also have to check that they also all align with the ones? Because now you only check the zeros. You didn't check if the whole formula would be one.
That's true, but so I guess it depends on your presentation. And this is the product of sums representation, right? So each individual equation can kind of, if it's, or each individual term, if it's violated, it will immediately force the entire equation to 0. Right? So if any one of these is 0, you'll get 0 for the entire thing immediately. For the ones, it's super annoying to check because you essentially need to see, does each case of 1 go through all of them, right? Right, so what you can do is simply check for the cases where it's supposed to be 0, and check if it's correct for all of these cases, and if it's correct for all of the cases where it is 0 and where it's supposed to be 0, then there's nothing third, right? Well, there's the third, there's the x's, but it's correct for all zeros, it's correct for all ones. Does that make sense?
Yeah. Yeah, if you also check where they're supposed to.
Right, so Right, so we did that, right? So we went through and checked, we kind of crossed off all places where these equations, where one of these terms would become 0. And we found that only one of them actually violated something. This is the case over here where we got a 0, but it's supposed to be a 1 according to the table. And then in the end, we also checked, did we cross off all zeros? So we did both checks, kind of. Is that good? All right. There's a Zoom question?
Yeah. Do we need to mark the redundant cases? And what were we supposed to answer to that question?
I mean, the question is formulated here as follows, right? Verify whether or not the given equation matches the truth table. Is there something that your friend could have done better? Now, the redundant equations certainly could have been done better by just not having redundant equations. They don't affect the truth table. Right?
The truth table is wrong because there is one term that was wrong. Okay, so that's the first thing. Second, you can also comment. I mean, you also pick up the points where, why are you making redundant equations? You have to work for those, right? Those have to be implemented. Those are gates. You have to write code, whatever. So could the person do it better, even if he fixed that mistake? Yes, there were redundant things that were not necessary. Remove them and the function will still be the same.
One more question.
Yes, but we could still simplify it, like it's not A, not B, C, D. If we just add this on top of it, it's still not optimized. So how do we know if we still need to optimize it, or if it's just okay to say, yeah, this is done, this is done, add this, even though it's still not.
Yeah, for those, we have, for example, methods like Carnot maps. You try to draw large circles, let's say, and also manipulate the axis in a way that helps your case. Here it's very difficult to say. For example, what you're saying is correct. It's a 4-term literal, right? Was there probably one where you could have merged it into the others? You could be sharp and see it. You could do some Boolean manipulations and see it. The K-map is a, let's say, more visual way to see it faster. Helps you.
Okay. Are there any more Zoom questions? No.
Oh, there was one. The one was asking, what was it? Yeah.
Is this comparable to the exam's difficulty?
Is this comparable to the exam's difficulty? So, yes, that's why we are solving it. But I'm not very sure if you think this is too difficult or this is too easy from the way the question is asked. It might be slightly simpler, it might be slightly trickier. It's hard to get the balance, but you know, we will have to ask some question related to Boolean functions, sum of products, product of sums. Yes. No. Yeah.
So in the exam, there will be a question about such Boolean equations. I would ask, can you do something? Is it sufficient to look for balances?
So if you find everything that is redundant, you have minimized that equation, right?
In this case, we did not.
Well, you didn't answer the question yet, right? So there's a part that you're solving it, right? Or
there's another question.
Oh yeah, there's coming the, hey, make it more optimal.
B is supposed to be answered already. This would be the answer. Or would be the answer. That's the answer we gave for B.
Yes.
Yeah, so in this case, the answer to B isn't the answer.
Well, you would have to rewrite the, I don't see it from here, just a second.
So
what was the question?
This is a product of sums form, right? I'm not sure if this is the most optimized. Probably.
Doesn't, I mean, B doesn't ask to optimize it, right? So there's the next question, right? This one. is a different question. It says do product of sums, not sums of products, and optimize it. Like the question is completely independent from the previous one. No?
If they ask, can you do it better, for example, they ask for, so just say, yes, you can do it better, right? It's like everything.
Yes, please answer everything that he can do better.
Just need to say already.
Yeah, I mean, it's a little bit difficult to answer this. The difficulty is I know what the questions are in the exam, right? So it's all hypothetical. What if this? What if this? So if you have a truth table where there is only one of the 16 entries is 1, what is a smart thing to do? Product of sums or sums of products? What? But one of them is smarter than the other, okay? So if a question comes and like the person has answered it the other, I mean, the solution, your friend did it the completely other way, you could quickly realize and say, hey, this is really stupid. I would have just done it the other way. And it's a quite smart answer, and it's probably what we are looking for. But you get points for things that are correct. There's not one answer to most questions. Okay? It's not convinced. Okay, this question is from an older time. I've gotten better because people complained about questions a lot. So the questions are more verbose. Takes longer to read so that they are less open to misinterpretations. Okay.
There is an additional question.
Oh, more. So the question is good. Are we always allowed to simplify Boolean equations with Carnot maps, or only if it's stated explicitly, you can always simplify it with Carnot maps? Why? I mean, it's a method, it works. If you like it, do it, you know. Oh, sometimes it is stated to explain something briefly. What is expected about the depth of our answer, since the solutions are sometimes quite detailed and time can get short quickly? Is really more than one sentence needed in such a case? Depends also on the length of the sentence, right? I mean, the guiding principle is the points that you have for the question. So what was the idea? 2 minutes, 1 point, right? So if we say one question is 1 point, we are considering that the answer should be 2 minutes should be enough for it. So if the question is for 10 points, it means that we think this question should, you know, take you 20 minutes, like you know, not rushing like crazy, but the average student should manage it in 20 minutes. That's our estimation, right? So we might be off a little bit, but if you have a question that is for 20 points and you answer it within 30 seconds, okay, maybe it should be longer, okay? So I'm speaking to you, it's a gentleman or a lady from there?
There's nothing new.
Okay. They don't even give a thumbs up or something. Disappointing. Oh, thumbs up, okay. I called it.
Yeah. By the way, to the person asking about the difficulty of these questions, don't be intimidated by me making mistakes, yeah? You're better than me. Also, I'm out of practice, so. Okay, no. This is what you're supposed to be doing now. A sum of products equation for the same logic function, which I hopefully have a clean version somewhere. There we go. Yeah, and you get the nice hint that you can use a Carnot map. Do you remember Carnot maps? So you have a two-dimensional table where you order the inputs A, B, and C, D in a gray code. Well, that was terrible. Okay, don't look at my table drawing skills. Okay, and well, this is clearly not a needed column. Yeah, so we're filling out this corner map with the desired output for each input. Yeah, so you have the input AB 0, 0 and CD 0, 0. So in this entry goes the output that's desired 0. Okay, then for the input 0, 1, 0, 0. Well, that's again terrible. We get a 1 for the output. For the input 1, 1, 0, 0, we want a 0. And for the input 1, 0, 0, 0, somewhere here, we want another 0. Okay, now I'll just copy off this corner map that I did earlier so I don't make another mistake. Is there a question how you do the corner map? No? Okay. Let me copy this off, and if there is a question afterwards, let me know. Okay, hopefully that's the correct corner map now for that function. Good. Okay, and now we're trying to identify groups of ones. Yeah. So, for example, we have a nice square. Yeah, the table wraps around, so I can use what? Yes, thank you. So the table wraps around, so we can do groups like this, right? It ends on the left and starts again on the right. So this group is identified by what? It's a 0 in A. Is it? Yes, yeah, I keep messing up. It's a, so the 0 in B must stay. There we go. The A doesn't matter, it can switch between 1 and 0. So we definitely need not B. And then over here we have the C that doesn't matter, but the D definitely needs to be 1. Okay, so that's our first term, right? Okay, you can also write the multiplication sign here. Okay, that's the first term that covers 4 of our entries. By the way, I just decided that these x's should be 1. Because I can choose them freely, remember. Good so far? Okay. Let me know when you see me making mistakes. Okay, another group here, right? Just always choose nice big squares. So you can pick this entire line as all ones also. And that line is identified by CD being exactly 0, 1. Right? And AB clearly doesn't matter. So we need not C and D. There you go. Well, I shouldn't draw a circle, I just wanted parentheses. That's the second term. And now what's remaining here is just one more term. But ideally, you pick these squares as big as possible. That means you write fewer letters in your equation. So, you know, if we just needed to cover that one, we could identify it by exactly 0, 1, 0, 0. But if we identify it by having 0, 1, and either of these two lines, we have more degrees of freedom and one letter less over here. Yeah, okay, so it needs to be 0, 1. That means we need not A, B, and we need not, is it not C? Yes. Yeah, it's not C, right? That's hopefully correct. Let me compare that to the master solution. Yeah, that's exactly what we're supposed to be getting. Amazing. Yes.
How would I read sum of product from the part?
You just invert it. Okay, you try to find groups of zeros. Like, you know how we earlier checked over here, we try to find cases where it's forced to 0 by one of them being violated. This works the same way, right? The sum of products and products of sums are just the complements to each other if you invert all variables.
Would I also invert the results? So if I read out not ED, then it would be E not D?
Yeah. So it's they both invert, right? So the output inverse, inputs invert. Yeah. I mean, it's what you do in the Carnot map is just a graphical representation of what you do with the table. So you could have also done the first question by drawing a Carnot map and realizing whether or not some of those rectangles were overlapping, so they would be redundant. Or you could have realized that a rectangle is covering a 1, whereas it should have covered a 0. But it's left up to you. I mean, the table method also works quite fast. You need to solve a few of those, so this is what it is. I mean, if you never solve one and you see it in an exam, it will take you 15 minutes. If you solve 3, 4 of them, you see it and say, okay, it's more of the same. Yes? It's a good question. I cannot. Let me think about it.
I'd say generally no.
Yeah, I mean, the question is, if you apply De Morgan to this, is it still the optimum solution? Instinctively, I would say yes, but I'm just trying to say. It may not work because of the x's. Because the x's I can take differently when I'm doing product of sums. And I shouldn't be I mean, I could do it, but I could have a smarter x distribution when I do sums of products. But without x's, I think sorry. It's a good question. Let me ask that in the exam. Prove that the De Morgan equivalent of it is the minimal solution now.
Any other questions?
What? It's a good one. I was promised a good question. This question has nothing to do with Boolean logic. No, I disagree, but okay. But I'd like to ask here anyways, what happens if we do a load word or store word? Okay. Store word instruction if the address is not divisible by 4.
Usually it's so when we use a load word and store word, effective address should be divisible by 4. And if it's not, usually it's actually a runtime error. So with assembler, usually you get an error while. And similarly, when you use a load half and store half, it should be divisible by 2. And load byte, it can be anything.
Yeah, but the instruction wouldn't let itself be encoded in having a not divisible for address. You cannot write the address.
That's also true. But yeah, so assembler what helps you to understand when you are simulating your assembly code using some assembler, software, that lets you know that something is wrong in your code. So, but that's true. When we
no, he can do it because it can be registered. Register could have any value.
I remember when my address was not divisible before, I was receiving errors from that.
Yeah, it's a good assembler, right?
Yeah, like the Mars.
Yeah. The thing that explodes. There's more. What is the best way to derive a NAND NOR gate representation from a Boolean formula or table?
So session is yours, actually.
Oh, session is mine, actually. I have to read from here and I have to answer from here. Okay, just a sec. So, how are you all doing? Everything okay? It will be over soon, okay? I mean, come on, it's not that bad. I heard the weather outside is nice, so appreciate you all being here. Some people care about the grades. What is the best way to derive a NAND NOR gate representation from a Boolean formula or table? Depends what you call best way. 5 moments. So what would you think is the best way? I mean, help me out. What do you consider best? Oh, yeah, what? Come on. So the colleague is answering easiest and fastest way, right? Easiest is probably for you important when you are solving the question. You don't want to spend too much time on it. And the question is, you have some sort of formula with chalk. Here is chalk. Stupid. Chalk doesn't go up. No, I have to do it electronically. Okay. So you have something like A and B plus C and D, right? So the question that is being asked is, okay, if you want to convert these two gates, you have A, you have B, they go into an AND gate, right? And then you have C and D, they go into an AND gate. And then, so this was this part, and now we put them into an OR gate. And if that's our output, there you go. So we made the AND OR gate kind of thing. Now, there's an evil question. Question? Okay. I like chalk. Can I not turn this around? Can I not?
Maybe I can write it on
there. No, I'll do it. Come on. Where's some paper? Oh, it's so much fun to write on. I don't know. That doesn't work. Okay. For those who want to enjoy the problem-solving session on their balcony, sipping a fizzy drink, I wrote the following: Z equals, does it work? Yeah. A and B plus C and D. So I said something like, you also see it, right? Oh my God. So this is the AND, so this is this gate. And then we have C and D that go into the AND. Okay. And now we are making the OR, which is this part. So this thing, okay. So this is that, and the output is Z. Now, there's an evil examiner. I should have written this larger. There's an evil examiner, and he's asking to do this only using NAND or NOR gates. And we do not see. We can handwrite our cheat sheet on the iPad, right? You see me grinding my teeth and saying yes. Okay. Any ideas about it from the class? Yeah?
The double negate, like globally, and then we use the modern to equal them.
Yeah, so that's actually a nice trick. So what your colleague says, we double negate, let's say, these outputs here. So instead of having this, so we have the AND gate, we invert it, and then we invert the input of the OR gate. So it becomes something like this. We are already sort of kind of there, right? So this is equivalent. Excuse my crummy writing. Agreed? Anybody disagree on this thing? No disagreements, everybody likes it. Yeah? Yeah, okay. So now the trick is, hey, can I convert this into something that looks more like an AND OR gate? Anybody? Yeah? Okay, so we are pushing the bubbles. These bubbles are being pushed here. What happens when we bubble push? The bubble goes to the outside and the operation changes. So this becomes this. Hop, hop. Ta-da. So here is double negate. And this is bubble push. And if you ask this, I mean, we can probably never get away from saying, hey, you can use also inverters. And if you say you cannot use inverters, you can always say, you know, an inverter is equivalent to any one of those gates, right? So you can take this and say, here's my inverter. No? The more interesting questions are, how do we calculate how many of the 30 points we got from the labs? I think there are 10 labs, you get 3 points each, and you know, if you did all of them, you got 30. If you miss one, it's 27. Do I miss something? So you have 10 weeks. Yeah, so that is 100. Now this will get scaled to 30. There was a question about rounding, you know, what happens if it is whatever 27.42, will it be rounded down to 27 or will it be rounded up? And you know, that 1 point is the 0.08 points in the, we will not do it to your detriment, okay? We will be nice. The assumption is that we are nice. Okay? No? Not super nice, like. Since we are discussing NATE gate representations, would it be possible to go over a relevant exam problem such as 2021 number 1A? No. It's not my exam, so you know, I don't want to look stupid trying to solve a question that I'll probably not manage to solve. Sorry. What is 2020? Does anybody have it? Let me just take a look. Maybe it's easy. I want to see the question before I say yes. Do you? 2020, spring 2020.
These are current ones, though. I think these are not the representative.
I know, but maybe it's a nice question. I'm also not sure, but I don't want to say no because maybe it's like super relevant and easy, and we can answer. I don't know.
Are those on Moodle?
They should be on Moodle, I guess.
I'm not really good with navigating this because
I'm also not so, me. I think there should be lab sessions. No, I did something wrong.
You just switched tab. Is it a lab session?
No, it's an exam question. There should be like lab reports. Lab reports.
Someone from here can answer us, actually, a student. I'm not sure where they are.
Maybe it's on the web page, on the DDCA web page, not on the Moodle. While we try to sort out that problem, any other questions? Yes, sir. Yes, sir.
I have a question to one of the exercises we solved earlier when you were there again. It was a Verilog exercise, and they gave us like a sketch of the circuit, and we had to write it in Verilog.
Okay.
And my question would be, do we need to name all our stuff and introduce redundancies in our code?
What do you mean redundancy in our code?
We write names multiple times or add files and stuff like that are unnecessary. So I would call it redundant.
I mean, redundant in the sense that when you synthesize it, they will go away. They are there just so that you can read it more clearly.
Usually in Verilog, you can write much code without naming it.
Yeah, look, if I understand the question correctly, you can correct me. There is, for example, a statement which you can write in multiple steps and have intermediate results, or you can write like one gigantic line. And when you write one gigantic line, you're not defining the in-between logic values. That's not a gain for anyone, because if you do it, it's not. You may think it is, because the longer you write, the more mistakes you make.
Yeah, exactly. If I write names, then that's even more.
It is easier for someone who's correcting your exam to follow your train of thought if you're doing it step by step. He adds, I mean, just like this thing, you can imagine that there is a longer formula and you write it like, I don't know, you have a complicated thing, you write it in one go, you mess up somewhere, and either it matches, it doesn't. And it's very hard to decipher. But if you have it like nicely written, hey, I do this, I do this, I do this, I do this, people can see it easily. You make also less mistakes. But it's up to you. Right?
Even if they are, the components are named.
Let's not, I mean, there are things that you have to make, you know, otherwise it doesn't work. For example, if you have two components you are instantiating, you have to give them distinct names so that you can distinguish them. No? Okay, as long as the code you write is correct. And in the end, the person who's correcting it is able to understand what you are doing and grade it correctly. And if not, it stands up to the, you know, to the session where you argue about it. Everything is golden. No? Ankara.
So why is the instruction JR, so the jump register, is an ARM operation, where we just use one register, which...
So R-type, yeah, I mean, it's semantics a little bit. R-type instructions are really, they take two source operands and write to another third register. So the idea is that there's a bunch of operations that fall into this pattern. So for that, they developed an instruction, and they said, hey, I need to encode these type of things. You add, you XOR, you AND, you do a bunch of things, you need this. So that's where that thing is needed. Now, there's a bunch of instructions, like invert is the same, right? You're inverting it, you are actually using 2 registers. Is it an R type, or can I make it an I type where I don't care what the constant is? So in the end, when the architects, so the people who are defining the ISA, they may have more problems with one set of instructions, what they want to put there, and they may realize that, hey, I need more R-type instructions, and anything that is not strictly 2 operands and 1 output, I will not use the encoding space of R-type. So they could have decided either way. No, how they define it. Implementation is up to me. So there's a difference between the definition, which is the architecture. When you say implementation, that is, you take the ISA description and you implement. It is part of the architecture, yes. And they may have done so, like jump register saying, is it an I type? It's an I type, right? Yeah, they said, could have been either. Because you only need 1 register there. I mean, it's not like you need 2. It's not like you need 3. You need 1. You have to put it somewhere. And importantly, well, this is a good question. This could come up as a question. That shut people up. One of the key ideas in MIPS was to reduce the number of different types of instructions. So you realize that you have a number of instructions which only need 1 register. You don't want to make an R1 type, R2 type, R3 type, because you say, hey, if it fits into one of the other types which I needed, I'll live with it. And the best example are the load word and the store words, which always have an immediate in it, even when we don't need it. So in the meantime, I think we have the question. Let me just take a look before we...
One question.
Oh, yeah, that's a bubble pushing. Push the bubbles left and right. So in that case, they did what? Oh, they first. Oh, yeah. Yeah, fair. Fair.
So what was the question?
This one,
Since
I
we're
think.
discussing, would it be possible to go over? Okay, so he wants to explain. See.
So, can we project this to here?
No.
She has to have it, right? Or no? Who is the? This one. We have to find it there.
Have you shared your screen?
Okay, in the meantime, there is something else. Regarding my previous question, in a past exam, HAB semester 16, there's a task 4B MIPS code snippets where we just subtract 1 in each iteration of our loop. But here, correct me if I'm wrong, the address is not always divisible by 4. But the solution claims that both code snippets A and B are correct. Could you please explain?
So I have actually opened the question too. Yeah, maybe you should. So this is the question.
Yeah. So the we are sharing a previous question, but there was a question from half semester 16. There's a task that was a mistake, so it should have been 4. So we made the exam and we realized that it's a mistake, and we the spirit of the answer was, yeah, you go through the addresses. And the idea was, is it better to, I mean, the reason why the question is there, is it better to subtract and check against 0, which you can do directly, or, you know, you have to continuously make the check. And the spirit of the question doesn't change so much for the constant. So for people, I'm not very sure what we ended up doing there. I think we looked at the answers. I believe, it's hard for me, it's 2016, I believe people that said both are right or both are wrong, both got the points in that case. I mean, it's a mistake on our part, the way the question is asked. Yes?
Andiamo a Portricceto. Andiamo a Portrì. Sì, hai guardato la strada? No, facevi qualcos'altro.
Greek? No?
It's not from me.
No, the language.
No, it's not Greek.
Not Turkish. Sorry, once again.
When the load word and store word commands are used in those types, sometimes the offset is not good. So it's just load word and to register without like an offset and then parentheses around the second line.
Well, no, I mean, that would be a mistake. I mean, there are no 2 registers, right? So it's
like it's used throughout all of those code snippets. So during the exam.
Let me just see a code snippet once again. If there is nothing, just assume that thing is 0. Yeah, it could be that it doesn't assemble, that's correct. I wouldn't be surprised if an assembler assumed if you don't write something, it's 0. But yeah, it's a mistake. It shouldn't be like that. Happens. No, you're writing it now.
No, the thing is that Zoom sees this.
But we cannot.
Not this.
I see. No, it's okay. I mean, then just to connect this again, we will write it.
I connected it.
Now it doesn't work.
Stop sharing. There should be something. No, I think the problem is with this.
Where's the here? Did we have the device projection? DocuCam. It's not connected actually.
What was this? I removed it and I put it back. But I don't know whether we need to do something else to make sure that it gets.
Yes, now it works. Ta-da! And now I need to question again, my God.
Let me share it again so that also Zoom sees it. Okay, and you can also see it from here. Is it okay? Yeah.
Okay, can you make it a bit larger?
Larger, right?
Perfect. So there's a horrible equation. Does it work? F equals to A and B. No, it's this one, right? The top one.
Yeah, this is the. Yeah.
So how does he go from there? Oh. A and B not plus C plus A and C. And now they say, correct the following Boolean equation so that it only contains NAND operations. Show your work step by step. Now, all I can do is I can go the same way that they did. One other version to do this is to try to push bubbles nicely and neatly. The other way that you can do it is to say, you know, for example, this is an AND gate, right? So there's an AND gate here. This is an AND gate followed by an inverter, and the rest we can play with. But the way they did it, and this is just Boolean manipulation, right? So they first come, my God, what did they do? The first thing they say is, okay, let's use a De Morgan on these two guys. So what we will do is we will invert them and we will change this. So we invert them and change the function in between. Now, the question is, how do you see where this is going? Don't ask that to me, okay? I'm not so good with these things. But, so then you have the rest of the thing is still the same. So we did De Morgan in one level. And now we have A and C not. So this is what happened. So the next step now is, let's see what they did here. They said, now let's play the De Morgan trick once again here among these guys. Okay. So what they will do is they will invert this. They will change the plus to and this will be inverted. So this is C naught, and this is A and B twice inverted. The rest we didn't touch, A and C not. Okay, so that was step number 1. Step number 2. Now, okay, nice. Sorry, we forgot the entire inversion here. What? So this one cancels to A and B and C naught. This one is A and C naught, and the entire thing is inverted. Yes, okay. And now the next thing they did is they said, let's try to take them into parentheses with the not C. So they want to change the parentheses here, and they end up being, my God. No, I will have to work this out once again. I'll just, quietly take this away, put it away, and just forget this ever happened. What is it?
It doesn't display your camera.
Oh, it doesn't display my camera. Excellent. So they didn't see how I struggled with it. Excellent. So Zoomland saw that I solved this perfectly. It's not really a question that I like. From the same sense that, if you see it, if you see the correct manipulations, you can do it. If you can do a lot of bubble pushing, you can do it. It's not, let's say, the most favorite thing. But just to give you a trick, sometimes if you are left with, does the Zoomland see the?
Your hand?
No. Zoomland doesn't see anything. They see this thing that you're sharing. So if I stop this, they see then, they see, no.
Nothing because the webcam doesn't.
That thing is blocked. No, I was just asking if I write something here. So one thing to realize is if you have a question that has only 3 literals, right? There was A, B, and C. So you can actually just write the truth table, and from the truth table you can work yourself way out. That's like once you realize what's the easiest thing. If you don't see it immediately, you can say, hey, there's only 8 different things that can happen here. You can quickly fill out the truth table. Once you fill out the truth table, you can then do the optimizations like you do on a standard Carnot map. So that's sometimes what I do. Not very sure how well it would work there. Yes?
We don't have to provide like a minimized version of the like circuit maps, right?
That particular question, I don't remember what it was. The one that we were looking at. So that, yeah, no, it doesn't say it's minimal.
Replace the OR by, you could just learn how an OR is using NAND, how a NOT is represented using NAND, and how NAND is represented using NAND.
I will manage the NAND represented by NANDs, yes. No, yeah, you could do it. But it's, from that point of view, it's not my favorite question. Nobody here is asking questions. Like the first two rows excluded. Okay, first row.
Okay, so for the load word instruction, basically we use one clock cycle to fetch it, and then get the date to the date of it, right? And then only on the next process we write it to register file. Because it's also a clock operation.
You're talking about, so the load word instruction is from the ISA. How it is implemented depends on the microarchitecture. So in a single cycle processor, so you have the address, you have the instruction, you construct the address, and you read from the memory in the book combinationally. The data comes out, and at the end of the cycle, you write it back to the register.
But this only happens on the next process, right?
Like every other, but there's no other operation that happens otherwise. R-type operations also work that way.
Yeah, sure, but what happens, for example, if I do load word one register,
Mm-hmm.
and then in the next cycle I do, I want to use that register.
It is already there, right? You wrote it already.
But it only came exactly at the time when we fetched a new instruction. We don't have like a race condition there.
It's a good question, actually. So if Zoom is not seeing this, right? Sorry, Zoomland, I'm just using the blackboard. I didn't manipulate it to use the blackboard. It just happened. So how shall we do this? So there is let's draw the clock cycles, right? So this is the first clock cycle. This is the second clock cycle. Something like that. And let's assume that we are having, this is the clock cycle, this is the clock edge that counts. Okay, and here in this clock cycle, what we want to do is a single cycle instruction. We want to load something into S0. Now let me not make the mistake. Something like that, right? So the address here will be loaded into S0, right? So at the end of the color, and then, so this is the one that I'm loading. And here in the next cycle, so that was your question, we want to do something like add immediate into S1, something with S0 and 4 or something like that. And now the question is there a race condition between this one and this one, right? Okay, so if you think about what is happening, right? So the moment the clock cycle changes, the program counter is updated. So you have the new program part. And so here you are fetching the instruction. So you're looking, we are doing load word. This comes from the memory, right? So the address comes here, we are getting it out. And now we are sort of kind of decoding it. So this is the decode stage. What I do, right? And then you realize that I need to find T1. I need T1. And I also have constant. And then here you have your execute stage. You say add these guys. And this is the address. And we go to the memory, we are not done, and get value for S0. And then here we write it into the register file. And so once the other clock edge has arrived, the value that is going to be S0 is ready. It's standing right here, saying, I'm here, I'm here, I'm here. And then the clock edge comes, and immediately after, tiniest of whole time delay, the guy is in there. And while this guy, and at the same time, the new PC updates, he's looking at the instruction, what do we get? And then he says, it's add-I, and he's decoding, and says, what do I need? I need S0. S0, S0 is already it's been years, it's already there. There's no problem with it. The problematic part is, once we start pipelining it, once we use different clock cycles to do these operations, while I'm decoding it, while I'm fetching, while I'm getting the operands, it may not already be written back. So this is when we start having hazards. But in a single cycle architecture, which is nice, you don't have these issues. Everything completes. The entirety of the operation is done, which is great. So there's no race whatsoever. Yes, sir.
I have a question regarding timing generally.
Okay.
Do you have any advice regarding practice questions, something regarding timing? Because you, in a couple of your older tests, you have some questions regarding propagation and contamination delay, but not so much any questions about setup and hold time constraints. What should we look at specifically there? Any advice?
Look, there is only two timing constraints, right? You have setup time and hold time. And for the setup time, for the how much time do I need it, for that constraint, you need the longest possible case, right, of everything. And then you have a hold time constraint where this problem is that signals can propagate faster. What happens if something comes very, very fast? You need to know both of these things because questions can come up and we'll assume that you know both issues. For example, it could come up with something like that. You draw a diagram, you write the gates and things like that, and they ask you, okay, how fast can you run this as a pipeline stage? Well, then you have to think, okay, I need that this gate completes, this gate completes, this gate completes. I also need the setup time of the register. From that, you get a cycle time. 1 over that is the frequency. And you say, hey, this thing will run at a gigahertz. Or they ask you something like, hey, draw the schematic, then give you the probe delays, whatever. Would this circuit run at 1 gigahertz? Well, you have to, put things together and then see if this circuit would complete in a nanosecond, the worst case propagation delay. Or they could ask something about the hold time and saying, is there a problem here? And then you look at the setup, you say, hey, it works at 1 gigahertz. You look at the hold time and you realize, hey, the contamination delay plus the contamination delay is less than the hold time. Meaning that if I try to run the circuit, there is a possibility that some signals will come before this flip-flop had any chance to realize what the previous input was. So he's trying to, your name is, and all of a sudden the new input comes. And because he needs hold time that the previous input stays stable there, if a new input replaces it before the hold time is over, we have a problem. And those two things you have to know. for a simple thing that we will ask them one way or the other, in combination, in something, but a little bit creative, a little bit less creative, but they will come, I think. Amelie Moore will come. We never fail to ask a question about me. Oh, there's a question. Yes?
And there was also a way to slow the processor. So this one to ask, what is the difference between
It's let me think. It might be implementation dependent, a semantic definition, because there are ways where you can stop this flip-flop from accepting new data. You have an enable flip-flop, so the flip-flop only gets a new value at the rising edge if there is an enable. And you can disable the flip-flop, so some input comes here, he's just not looking at it. It's just like you put a blind in front of the flip-flop, he opens his eyes, but he sees nothing, or he sees the previous input, and he thinks nothing has changed. So that's what you use for stalling. Okay, so you physically stop the propagation of the data by disabling the flip-flop. In the no operation, you actually don't stop this guy from operating. You just put an operation that will not make any difference. So instead of trying to say, well, I'm not going to stop this thing, I'm just going to do something completely irrelevant. They serve the same purpose, because your purpose is that the next instruction cannot go and we need to wait. So either we somehow manipulate the entire pipeline. So if you think about pipeline in the car manufacturing kind of things, that, one piece comes, there's this like cartoon character welding it, the other guy hammering it, whatever, and then they pass it to the next guy. So in one case, you press like a button and say, stop, everybody, after this part, because the other part you want to go forward. Please, guys, you stop, you guys go forward. And in the other one, you just, while this guy is passing to the next one, you say, psst, I have a parcel, no operation. You just give a funny box and that thing propagates through. So one step of the way, he's not doing something useful. That allows the other part in the pipeline to finish its operation. So, it's actually a very good question, but I don't think we discussed this in class. So these detailed questions, unfortunately, are not part of the question. So the trick is, who does this thing? Who solves the data hazard? And the compiler can solve it, because the compiler may know what the architecture does and may realize that these instructions, when executed one after another, will have a data hazard. And the compiler, while he compiles the program, may already schedule them so, and usually they will try to put a useful instruction. There's no point in inserting a no operation. But let's say 80% of the time, they will be able to reschedule things so that there's no data hazard, and 20% of the time, there's no other solution, and say, okay, well, whatever, I'll just put a no operation in there into the code. But that's at compile time. The processor has no control over this thing. And this assumes that the compiler knows intimate details about how the processor was implemented. Now, this is not as difficult as you can imagine because there are some processors which are in your tablets, cell phones, etc. Those are things that sell in the millions. They are very common. So the processor may realize, the compiler may know exactly what is happening. However, if you're a hardware designer, you cannot let a hazard happen. So even if the compiler can take care of it, you cannot rely on the compiler doing the right thing. Because, in the end, it's the processor that executes the program. And if the compiler slept or was not paying attention, you cannot be held responsible. So in most cases, the hardware would still check if there's a data hazard. And now it's an implementation question. What is easier? To hold part of the pipeline by doing what I said, or by inserting a bubble by doing let the pipeline run, but insert in between an operation so that part, there's a separation between the leading instruction and the following trailing instruction. Because what you want to do is separate them a little bit. Let the previous instruction go further in the pipeline so that it can write the result that the trailing instruction can use. So either you stop advancing it and artificially stop things, or you just insert something in between to artificially make a gap between them. And that's, at some point, is also a hardware implementation question. There should be a limit of... Okay, go ahead.
So why do the hardware designers decide to use the stalling in the when they design the CPU instead of inserting a no-op?
I didn't say they would do that.
No.
They could do both.
Because to me it seems easier adding no new wires than just adding the no-op.
Well, adding a no-op is also sort of kind of not, there's still effort involved, but there are cases where you need to stall individual pipeline stages for other reasons as well. So the stalling mechanism may not be only there for the data hazard, you might have other issues. And in real processors, actually, the one lie that we are telling you, or somebody was actually alluding to it, these memory accesses do not happen very fast. So we actually end up waiting a lot for the memory accesses, sometimes tens, hundreds of cycles before we can do anything. So a lot of the hardware needs to be stallable. But they could have also done the no operation insertions, but stalling is more energy efficient because rather than, letting the car run idle in front of the red light, you just turn it off because, there's a train passing, like a slow train. So it's kind of, question from not the first row. Great.
So, do I understand correctly that no operation is something you do at compile time? So compiler detects that there might be a hazard, so you insert this no operation and the stall process, that there is something you do during runtime. You detect some logic somewhere that, oh, I'm going to use this register, it's not written yet, so the logic I put this name from here to 0.
Mostly correct, yes, but the hardware, you could have also inserted a no operation in hardware as well. But it's not possible in the instruction set to make a stall. The compiler cannot make a stall for you, but during compile time, you could realize the scheduling of the instructions that you might have read after write hazards, meaning that, hey, I'm reading too soon before the write has completed, and for that, he might try to push them apart. And the goal would not be to insert knobs, but that's like I tried everything, but now I have to. Usually you try to put something in between that sort of kind of helps you out, like something useful. Sorry? You don't reorder them. You just, I mean, reordering is another example where you do more, and most modern processors would do reordering. I'm not saying this is not the thing. So if you look at any modern processor, they play so many tricks. It's crazy. But in the simplest term, inserting NOPs, there are two instructions that follow each other, and they enter the pipeline. And let's say this takes 10 cycles, this takes 9 cycles. And you realize that this guy would only write back in the 10th cycle, but this guy is coming too close after. So you need to separate them. You're not reordering them. You just say, let this guy wait a little bit. And what shall I do? Either you completely stop the pipeline from operating, or you say, here's something to keep you busy. It hurts no one. You're doing a no operation. The operation will not change the value of anything. You are adding 0 to a register, for example, whatever. Does that make sense? You know, so don't get confused. I mean, I'm answering the questions not for exam's sake. I'm answering the question for explaining the thing. As we discussed, or I tried to put on those slides, unfortunately, we didn't cover the more advanced parts of the data hazards and things. So, you know, it's the amount of things we can ask there is a bit limited. You have to thank Mohammed for that. I mean, he promised in front of the class, right? So, promise is a promise. Anything on the Zoom land? I didn't. They're upset? No? Here. Yeah, I didn't write much on the board, so I'm very sorry. Some of us are abroad and could not join in person. As long as the weather is bad there, no problem. How can larger memories be constructed out of individual memory blocks? Can you show an example? Wow, without, nothing works for the... Can't we turn the camera on from one of the...
Ah, you can, I guess. Yeah. Okay, let me make this. No. Yeah.
Ah, now it works. There is this thing. I see this thing.
Right now it's all right. Yeah, they can see it, right?
Can you see my hand?
Yes, but they see so right. Exactly.
No. Yeah, let me.
So they have to.
So they're asking a question from the Zoom if I can show how to make it. We're just trying to figure out how they can see what I explain. But I think they see something.
They can see it on Zoom. They can see it on Zoom. Maybe on Zoom. If I share my screen.
So other questions that don't require me writing, so let's answer them. But oh yeah, sir. Yeah, how can we do instructions? So the instructions change the state. They change register values, they change memory locations, and they change maybe flags like overflow and things like that. So anything that might have happened, you have to take back. You know at what point you have to go back because you know you're executing a program and you just flush them and redo. It's in most of the cases because the control hazard would mean that you are going back to another address. You are not going to what you already did. but instead of that, you are going to the other address. Now, the hazard units are aware that these things can be happening, right? So they actually, there are tricks like not committing in the load store unit. They have a unit that loads and stores data. They mark what they did so that they can replay it. It's costly, and the deeper the pipeline is, the more costly the operation is. If you have 3-4 pipeline stages, the control hazards you can have is actually not that much, because the other instructions did not yet update a memory. A memory write is usually the very last thing that happens. So that in that case, you are very lucky. Does that? Well, it's not nice. So this is also why making, pipelining looks like a very, very good idea. But the moment you go 20, 25 stages of pipelines, and you have all these superscalar processors that can do more things at the same time, there's actually a lot of instructions in flight in 25 clock cycles. So if you think that a processor is 4-way superscalar, meaning that it can do 4 things, and 25 cycles, there's 100 instructions already running. Chances are very large that there are some branches in there. I mean, hardware designers and programmers, we like where things are very regular and you just read from memory and we are very good at that. But unfortunately, there are linked lists, there are all kinds of funny things. Life is not so kind to us usually. And in those cases, that hardware is, for example, very acutely aware of these things happening. It needs a very, very strong branch predictor and a very fast recovery in case things don't work well. Okay.
I also asked to the chat for drawing on the blackboard an example of what you just said.
How can larger memories be constructed? Okay, but the Zoom land doesn't see it.
Yeah.
How many people are on Zoom? How many people will get upset with me?
32. Maybe their colleagues could share their notes with them and no one will be upset.
Maybe. Is that okay? How many people are here? 1, 2, 3, 4, 5, 6. It's like 50-50. We cannot turn that one doesn't have a camera, or your
has a camera. So
okay.
What do you recommend that we show?
Yeah, we just show the part of the screen. I mean, if you share screen, you share. Yeah, that would work.
Can I share the screen? No,
you just want to turn on the camera, right?
The camera is
on,
but I don't think they will be able to see a lot.
Yeah, they will see something.
Okay.
Can I?
Yeah.
Is that power?
You can be out of power for a while.
For a while. Whoa, it didn't. Oh, it did. It's okay. No. Can light, room. My God, blackboard. Okay. Now the trick is, from the Corona times, the trick is to give me an indication of until where I can write, like this. Yes, and like this. Yes. Is that working? Okay, this will have to do. So this area is okay. So the question is, how can we make a larger memory from a smaller memory? Right? What? Okay, so there are two. So okay, let's draw a small memory. Let's say we have 8 address bits, and we have 32 output bits. Okay, so this is DI 32, and this is DO 32. Now, how many entries do I have here? Huh? How many words? No. Maybe 8. Okay, so I have 8 address bits, so it's 2 to the 8, that equals to 256 words. Each one of them are 32 bits, or 4 bytes. Right? Agreed on this? So that's a 1 kilobyte memory. How do I make a 2 kilobyte memory out of a 1 kilobyte memory? Does that make sense? Okay. So first of all, very simple thing, I need 2 of those, okay? There's no magic. So if this was mem, I need mem, and I need mem. Now the question is, how shall I connect them? So I still want a 32-bit memory. Is that okay? No, okay, let's make it very simple. If I need a 64-bit memory, I could do the following. I could take the 32 bits from here. I could take 32 bits from here. The address 8-bit goes here. The address 8-bit goes here. The data in 63 to 32 comes in here. The data in 31 to 0 comes in here. There you go. Did that make sense? The trick here is the output, I want 64 bits. I realize that I have a 32-bit memory. And I say, okay, I need 2 of them, 2 kilobytes. And I need to make it in this way. I mean, it's very simple. They use the same address. This guy gives the upper 32 bits. This guy gives the lower 32 bits. So if I'm writing in it, the upper 32 bits goes here. The lower 32 bits goes here. But they have the same address. Okay? So that's solution number 1. Solution number 2 is a bit trickier, where we say, yes, Frank, but you know, that was a neat trick, but I need 32 bits. Okay? Does it make sense? I need 32 bits. That was a mean trick. Then you say, okay, I still have to have 2 mems. And they still have 8-bit addresses. And, well, the data that goes into them is also the same. So this is 31 to 0. But now the output, it can either come from one or the other one. So 0, 1. And this is 32. This is 32. And this is 32. Right? Now the question is, what selects it? And you say, hey, there is an additional bit here. This additional bit is actually an address bit. So 8 of the address bits come from here. 1 of them goes here. Now you can say, is it the least significant bit or the most significant bit? Or is it a bit in between? What do you say? Who says most significant? Who says least significant? Nobody says least significant. Oh, come on. Who says it doesn't matter? Yeah, it doesn't matter actually. It matters if you are in Safari group and you're trying to do RowHammer, because you know which memory address is next to physically which memory would change according to how you assign these bits. Because data will be written either 1, 2, 3, 4, 5, 6. 257, 258, 259, or it would be written 0, 1, 2, 3, 4, 5, 6, 7, 8, or any other weird combination depending on which bit you pick. But what happens is the address bit is 9 here, the output is 32. So this one is 512 words times 32 bits. And this one is 256 words each 64 bits. They are both 2 kilobytes. Yes? No, no, no. Don't ask a stupid one.
Doubles the storage if data we are storing is the same each memory.
Once again?
Don't we need 2 separate inputs for each memory?
Here you mean?
In the 30-bit version.
No, because I'm either writing to this one or to this one. So there is actually, let's say, write enable also going depending on the same bit that goes here. So that's a good one. So you're writing either to the left one or to the right one. That's a good one. Full points. Frank, half points. Frank, half points doesn't mean that everybody else gets double the points, okay? I fit into the board. But the person asking was here, right? I think. Is that okay? We put so much effort into this. No? I did it for nothing. Oh, okay. They're being just kind. They thought it was great.
I'm just understanding correctly how the write enable and the sort of read enable work to select which memory you are selecting to
Yeah.
write to and to read.
Well, the read, yeah, whether or not you have a read enable is questionable.
Somewhat of a read enable because we select just which memory. So
Yeah.
yeah, yeah.
Yes. You, yes, yes. Yeah.
If you were to increase the size, would one multiplexer which then takes multiple inputs, or would you chain multiplexers to then choose the correct memory bank?
I mean, so if I understand the question correctly, I'll just delete this part, or I'll delete this one, okay? I mean, that one was simple, come on. So if I understand the question correctly, what it boils down to is this 0, 0, 0, 1, 1, 0, 1, 1, and these 2 bits, different than, let's say, doing this. Yeah. It's I mean, technically, when you draw something like this, it might be that, remember there was this lecture where we didn't talk too much about it. It is actually possible to make a 4-input multiplexer as one gate. So you could internally make it, but it's not really relevant, right? I mean, they are both equivalent, whether or not you use this thing or you use this thing.
So a question regarding
Okay.
Basically, we say that we apply our inputs after the postage.
Mm-hmm.
And I get we don't want to apply it like while the postage is changing, right? Because then we can have some weird things happening. But the question is, why do we apply it after the postage, not before? Because if you apply it after the postage, then like the circuit doesn't see these new inputs, right? And you only get the
That's actually a very good question. That's a very good question. It's an excellent question. Let me, this still works, right? Yeah. You poor guys are waiting for the laptops to free up so you can go. Okay. So the question that is being asked is that when we have a test bench, we discussed that we should apply the input. So if this is the rising edge, we should leave some time and apply the inputs a bit after the rising edge. And the question is, okay, we get it. Maybe I shouldn't be applying it right when it changes, but why don't I apply it before? Okay, so the trick is I apply the inputs so that for the Moore machines, where the input doesn't change the output, this input will get sampled by this edge. This is my goal. And because I have a setup time, I want to give it as much time as possible, so I'm pulling it back as much as I can. At the same time, I'm trying to stay away from the hold condition from the previous one. But I'm trying to, ideally, I'm trying to position it in between for the Moore type operations. Now, I also have Mealy type operations. In the Mealy type, the present input could directly change the output. So if I sample the output here, so this is my output, I also want to give enough time so that the output can be calculated properly in the same cycle. So this is the reason why we are doing this. Now, in real life, when we make test benches, the whole time is usually tiny, tiny, tiny. So people say, why don't I just put it just as much as I can before? And then when you come to a real circuit, where circuits have delays, the clock, we have a number of issues. The signals inside the chip can get delayed a little bit more than what you expect. That's why you don't want to be too close to here, because it's just like it's a high rise. It's like, oh my God, I'm going to fall down, right? So this is a setup edge that you are afraid. And you say, oh, okay, this is too high. But you walk backwards and then, it's too high. So you want to be actually in the middle of the thing. Anyone been to Norway? Norway? No? Anyone from Norway? No. No. You've been to Norway? Okay. The reason why I'm saying Norway, there is something called the Palpitz Rock, Preikestollen. It goes like 600 meters down on 3 sides. So if you're on top of it and you're too afraid of one side and you're backing down, it's 600 meters the other way. It's a ridiculous place. Okay, sorry, go ahead. Yes. Nothing actually, if you think about it, but if you are to construct it out of gates and things, ORing is a simpler operation than adding. Because in the add, there is a long 32-bit carry chain. In the OR, it's just a single, there's no delay. It's a simpler operation. It comes out of those, let's say, back in the good old times when we were drawing circuits by hand, we didn't have cell phones, we were caring about optimizing these things, and glaciers weren't melting. No. But you are right, it could be done in a number of different ways. It's not the only way to do it. It's just a convention because execution-wise, operation-wise, it's a simpler operation than adding. Okay.
You can continue.
Yeah, so the Zoom session is dying. I'm sorry, because the computers are going away. I might try to join to the Zoom session myself. I could, right? You sent the Zoom link? Let me see. Well, if you want to go, you can go, obviously. How many people are on Zoom? How many of them are actively on Zoom? Like they're in the balcony. Where was the... here, Zoom. think.
Find the link?
I think so.
It's the same as the class one.
It just doesn't start.
Just wait a little bit.
You can go. I mean,
Yes,
you have to assign me the session.
Yeah, that's what I'm trying. Let me just.
I am not in
make
yet.
sure that you have this correct link.
You can invite me.
I can send you the link.
Yeah, but I think I have it. Oh no, 6975. Yeah, I have the link. It just doesn't.
I'm not sure why you cannot, because I'm on its own.
Let me just disconnect and connect again. Your connection was interrupted. Reload.
So there is an internet issue.
Hmm? Yeah.
You were disconnected.
Oh no, there's no network here. There's no. Now again.
Maybe one of the students.
They can just listen from the microphone from there. Us working for the network issues has convinced everybody to leave. The question is now, are we feigning to do this? I'm looking for an Ethernet cable. Is there? There's an Ethernet cable. Okay, it was useful. Wasn't horrible. Open Zoom. It's connecting. It connected. It's. Okay, I think I'm in. Can you can you assign me the host so that I can use the audio from here? I'm the host. Okay, can you turn off the microphone? Can you just mute? I don't know, can you... Now? No.
I'm muted.
How is this? Now? Yes. Yes, yes, people, I managed it. Unbelievable.
Host.
I am host. I can do everything. You can just enjoy your meeting. Okay. So I don't have the microphone. So those of you who are in the very back, if you want to have questions, come please closer. Please. Millie Moore. 100%. No lying about that. Millimore will be in the exam. There will be a question about milli and more.
Only one?
At least one.
How many?
Wow, what is this? Like a bargaining table?
Yes.
Do we know how many questions are? 7, 8, something like that. Enough to keep you busy.
At 17, but I'm not sure if you
Hmm?
we discussed 17, but I'm not sure which ones.
Oh, but some of them are longer, some of them are short. So the idea is that, what is it? We have 70 points, right? And we said 2 minutes per question. 2 minutes. That makes 140 minutes. Right? The exam is 180 minutes. So in theory, you can gingerly make it. That's the theory. And what we do is we now prepare some questions. We are putting it together. We are checking if there are no obvious mistakes and things like that. And then 2 poor souls have to solve it and report back to us how many minutes they have with each part of the thing. That's how we, we choose people who have not been doing this forever.
Can we sign up to that?
And those people, and based on their feedback, we adjust, the points and things like that. And most of the time this works. However, it's not an infallible kind of thing. The suggestion is, if there's a question, whatever, 7A, and it says 10 points, we really thought that this needs 20 minutes to solve. And if you're solving it in under 10 minutes, it might be that you are really, really good or really quick at writing, or happen to write the exact question on your iPad written, whatever, cheat sheet. Okay? Or maybe you're missing something.
I don't have those questions in the exam.
Why? What? It doesn't make any difference. Why don't we have bonus questions? Oh, sorry, Steve is here. Steve is. What's the boundary for a 4 and a 6? Okay. Let's just stay there. Yeah. Sorry, bonus question. It doesn't really make too much of a difference, because in the end, what we want to do is, it's a simple problem. You want to assign grades 4 to 6 to individual people with 0.25 granularity, right? Like how much? You're not getting a 7.5. Okay, so if you answer all the bonus questions, you can't even show off. It's a 6. It doesn't go to 6.5, 7, 7.5, 8, 8.5. Like why? Why bother? No? What's the boundary for a 4 and a 6? So we actually have an idea. Usually what we want to do is, so this is a 6, this is a 4. A good exam has a distribution that looks like this. Okay, and that's on me, making the exam good. If I make the exam bad, so these are very bad exams, right? So if I have a distribution like this, it's horrible. If I have it like this, it's also very bad. Actually, you know what is really bad are these ones. Those are horrible. Because, sorry to say, but whether or not you get a 5 or 5.25 is not going to make any difference in your life at all. Maybe having a difference between 3.75 and 4, you could argue about that, but they don't matter at all. But, it's a very ugly thing trying to say, okay, it's clear that somebody who gets, 10 out of 70 should probably not be passing this class, right? I don't know.
I got the two binary numbers correct.
Yeah.
No, I mean, you have to trust us that if the exam results come out like this, we check it actually, right? I mean, this is our goal. I want to have an exam for 400 people that I don't know. I'm asking like a couple of questions. They sit for 3 hours, they come back, and 400 people magically fall into this distribution. Then you feel extremely good about yourself. It's not like, haha, these are fair. No, it's not, you know. It doesn't matter, you know, what grade you have doesn't really matter. I mean, you'll do great no matter what. The goal of the course for the grading is not to be the reason why you failed the block exam, also not to be the reason why you did bad in everything and you just, you know, were pushed through by this lecture because it's a service lecture. So that's one of the clear goals. No? Yeah, for us, it's a nightmare because if I have a question that everybody either gets completely right or completely wrong, so it falls into these things, it's really bad because it you know, screws this thing completely up. And so, you know, we have I have nightmares about, you know, having a stupid question. The worst thing that happened in a DDCA exam, you know what happened? It was not the big one, it was the winter one. And we started the exam. It was a bit more than this amount of people. We distributed the exam sheets. And we started the exam, and one guy raises the hand and says, yes, what's up? He says, the solutions are here. Yeah, happened. Actually, to be honest, I'll be very frank with you. It's good that he snitched because it would come out eventually, right? And we would have to redo the exam. So those people would have to show up at another point, and then we would have to most probably hastily do another exam. And when we do hastily, those, you know, adjustments that we make are a bit, you know, not done as well.
Why did you have to like person report that?
Well, he did it within like a minute or so. We said, okay, guys, please stop it. We distributed you the things, and everybody was nice. We collected them. I was in Hungaberg, frantically trying to find a printer to print 30 copies of the correct exam. It worked out. It took like 40 minutes longer.
So some people had seen some solutions, right?
Yeah. Yeah, I agree. None of the exams are completely fair. I mean, to be honest, I mean, some of you know the subject very well and would do very well in any kind of thing. It's just that the written exam organization doesn't work for you. You get stressed, you get upset, you don't perform as well. Doesn't mean you are bad or something. I mean, I see it more as a feedback to you, what I think. You know, I try to ask some fun questions so you can judge yourself how well you think you have had it. And in the case you get a, let's say, grade less than 4, I mean, it's a problem if you thought that you were getting a 6 and you end up with a 3. It's a problem, right? Because you thought that you were like the master of this thing. And for whatever reason, there is something wrong. It might be that the exam is horrible, could be. But it's a feedback to you. So if you are more interested in these topics, maybe you should revisit some of the things or, you know, invest some more time in this. If you're never going to look at it, you say, okay, you know what? I now know why I don't really like this thing. Like, fuck this DDCA, and you're done with it, whatever. No? Seems fair. But I see it more as a feedback, not like, you know, oh, you have a 6. Oh, my God, you're a great person. You have, what's your grade? 425. Oh, we have... We have a core course, VLSI 1, and we actually ended up hiring one of our students as a PhD student from our course, and the person got a 3.5 from our main HDL design, so VLSI 1. The person got a 3.5, is now a very successful PhD student with us. You know, it doesn't mean much. So at that time, when you have a, let's say, a grade less than what you think you deserve or what represents your level, you
you have to think about what was it? Did you study enough? Was your preparations enough? Did you maybe not understand all of the things? And if you know what's wrong, then everything is okay, you know, in your life.
When you took your exam, you just make sure to check
what?
Check the connectedness of classes. It's inside focus.
No, honestly, any of your grades won't matter when you graduate. If anybody at any work that you're looking for an employment is going through your CV and looks at it and says, but you got a 4.5 from the DDCA, that person was trying to find a reason not to hire you, okay? I mean, if it falls down that way, there is something wrong. You didn't impress at all. So the last thing that you did, your master thesis, the recommendation of your peers, of your supervisors, your master thesis, your bachelor thesis, those are the things that will represent you when you apply for a job, for a PhD, for future employment. Not, I mean, say, hey, they went through the classes. Yeah, okay. You know, if you have someone who's applying in the first year, he's got 4 zeros, 4, 5, and then, you know, picked up throughout the year, said, yeah, he was into partying too much in the first year, then got her act together and whatever, look, that's a great master thesis and I'm hiring him, her, whatever. No? Now you still like me, wait until the end. Zoomland, sorry. Zoomland is only 25 people still there. Bots? So do you know Steve, Ruben? Oh no, they are leaving. Oh yeah, there are some of them are dot because there is dash, there is a, there is dot. And we are awake. Sweet, sweet, sweet home. I hope it rains there. No, it's okay. Friday afternoon. I mean, I can stay here, don't worry, but shall we call it a day? Okay, if you have questions, feel free to send emails. Some of you are sending emails. It's better if you send it to Moodle because other people may have a similar question and they might answer it. If a Moodle question is not being answered, write to me and say, hey, Frank, what the hell? You said you would answer it. You're not. Yes.
You know, the old exams where there was like
yeah, I know.
I mean, do you have any personal thing that you would say that could be?
I wrote down this thing.
No, that could be that. But I mean, do you know something where you would say like on what can we maybe practice? You know, normally you can practice.
I mean, the exams are good. The questions are good. It's just that it was a bit silly what happened in the lecture, that the pace of the two lectures were a bit different. And you have to understand, Onur gave instructions to the students to tell the lecture in a certain way. And we didn't really think about how that would affect the exam. And there were a lot of, let's say, concerns. And Mohammed said, hey, let's not do it. The unfortunate part is if you look at the previous exams, we have a lot of cache-related questions. Or we mix, for example, some of the HDL questions, Verilog questions with the caches together, or the performance questions, because that was a good thing. But since we promised, we are not asking anything from the first thing that happens is, oh no, we don't have caches. What will we do? So I'll have to ask more from the previous ones. But I mean, when preparing the questions, I also went through the PowerPoint thing and said, okay, what did I promise to do and not to do? So
maybe as an exercise, still solving the old exams, just solve the ones which are relevant.
Yeah, I mean, the exam questions are, I mean, some of them are actually good, interesting questions also for you to learn the material, right? I mean, in the end, okay, the caches are not being asked in the exam. Shouldn't you know about caches? I mean, as a computer scientist, it's actually a very relevant and important thing. So if there's a question that also involves the cache, you know, what's the compulsory limit, what's the capacity limit, what's the, you know, how do I calculate the average memory access time? How does it relate to the speed of the I mean, it's a good thing to learn. I mean, it's not wasted time. It also, if you're answering those questions, you can also answer other questions more easily. It's not wasted time at all. But yeah. So if you say that I'm going to spend 100 minutes on this exam preparation, I cannot wait to learn things that will not show up as a grade. Yeah. You'll do fine, don't worry. No more than 6 for you. Okay. So if you have any questions, feel free to write. Try to enjoy your days. Don't obsess over it too much. It will be over. Trust me, if I wanted you failing, I would ask really evil questions, okay?
I lack of right on that number, I can see all the lines because that's it. I've uploaded, but download it again and had some second there and not written my TA. I don't know if you want to express it. He has some type of facts.
Well, put Mohammed and after that the same name. So
Brian, do
okay. I mean, it's your right. I mean, you know, don't be upset about it. But if they are not responding, the head PA in Atabak and Mohammed, so make sure they are in CC. Okay. It could be that, you know, in summer, some of them go to holidays. Bye. Cheers. You don't want any extra points, right? For all the work you did? No.
I mean, it doesn't hurt if you do.
That is okay. So they might be on holidays, they might have other things. I mean, yes. Okay. But if you put their superiors there, they would say, "Oh, okay, they are complaining." Okay.
Yeah, that's good. Thank you very much.
Cheers. Bye. So, yes.
I have a question for this.
Sure.
I think it's out there. What's your t-shirt size?
What's my what?
T-shirt size.
What's the t-shirt size?
T-shirt.
This one is XL.
Okay, you're very fixed.
Well, depends. Sometimes I don't fit into XLs, which is very, very annoying if you cannot fit into an.
What one would you prefer? So I have 2XL.
You know what I prefer is that there's a t-shirt M, I wear it, and it's very good. You know? But I had a few colleagues from China, and they were also, you know, saying, we want to give you a t-shirt.
Okay, so what do you wear when you buy something from Turkey? That's what I.
You know what ended up being the t-shirt size? 6XL. Yeah, really. But the choice was between 4XL, 5XL, and 6XL.
Well, you know, I had the opposite problem in Britain. I also bought a shirt. It was a small. I don't fit in the small. Like I'm normally a large. And the small was at the same size as my large.
Yeah, that happens also in Turkey. I mean, if you go to Mavi, I buy a lot from Mavi, for example. It really depends. Actually, they have also all these slim cuts, relaxed cuts. So I've known that L was large. I've known that XL was too small. So you have to try it. So for example, this is a conference I have to organize. They actually said, I need a large one. So they actually made an XXL just because I was saying, hey, you are discriminating against large.
An XL, right?
Then it turns out that their XL was actually even, I mean, this is even quite large for me. And the XXL is really, really
But you
large.
would wear something that is nevertheless too big, right? It comes from one of your students.
You are not allowed to bribe us. You know, there's a law.
I'm not going to bribe. It's going to be everything going to happen after the exam, after I get my results. If you don't have any.
It depends on whether you depends on the results.
We are federal employees. It's against the federal law. There is a limit at what we can accept gifts. I'm not just joking.
It happened to me also, but they also did this last semester with different professor. I think it's 30 frets. So you have to make sure that you find it efficient. Turkey, so it won't be okay. I'm just saying. Okay. Is that nice? It will be customized, but that's fine. Oh, customized! Oh my god. Okay, Zoomland, I'm shutting it down. Sorry.